quickly into the model-based environment. So, model-based reinforcement learning. So, first thing that we are going to do is to just study model-based. And as I told you, so we are going to recap here. So, the ultimate goal that we have is to just find the optimal policy, right? So, you want to know, upon seeing one particular state, what is the optimal strategy that you should do. And we talked about it that we have two major issues here. The first one is that if you want to compute that value function, what is the optimal policy is the one which maximizes the value function, right? And how I can compute the value function? Well, I essentially need to know at each state how I'm going to transit to the next state and how I'm going to get a reward, right? And this means that I need to be able to describe the environment, right? So this is the first challenge that we have, how we can describe the environment. And second one is that what if the state space is huge? So the second one, you forget about it right now in this chapter and the next chapter. So 2 and 3, we just talk about tabular, where we think that the state space is not too large, or is still we are able to handle it. Then we're going to see how we can handle the second issue in chapter in the second part of the course when we start with the deep reinforcement learning. But at this point, what we want to do, we want to start with the first question. We want to find some tricks that we can evaluate one policy, for instance, in one environment. And as I told you, there are two different approaches. One of them are model-based. This means that we either impose one statistical model for the environment, or we know it based on the nature of the environment. For example, in this frozen lake example, you can describe it, right? It was a very simple categorical distribution, right? That is not a hard thing. But if you have a real robot, this is then a bit of challenge, right? So this is what we're going to do in this chapter. Next chapter, we're going to start with a model-free, where we accept this fact that we don't have access to that model in general, and now we want to just come up with an approach to estimate. So when we talk about model-based, as I told you, we assume that we can mathematically describe behavior. So we either know it because of the nature, or we are able to just we just impose it on the model. So this was the dichotomy that I told you last time. So this other gray part of the table is going to be chapter 3. But I know what we want to do. We want to talk about the model-based, and in particular, we want to understand if we have this power to describe the model, the environment very concretely, what would be the optimal policy, right? What is that? So we're going to see that there is one specific optimality constraint known as Bellman optimality, which comes directly out of the recursive property of this value function. And then based on that, you can guarantee that you always, in such situation, have an optimal policy, and you can eventually compute it in most of the cases. Okay? So this is what we want to do, and then we're going to see how we can practically compute it when we know them, which is basically the two value and policy iteration algorithm. So now, let's start with the model-based approaches. And the key factor in the model-based approaches is that we assume that this Markov chain that is describing the transition from one state to another, we do know it. Like we have access to it. We can literally write it down. So quick recap, we talked about the Markov process, and we said that the states are describing a Markov process, right? This means that when you start from state 1, then at time 1, then you're going to change to another state, and you keep on going like this, right? But every time that you want to know what is the chance of going from this state to the next state, as long as you know what state you are in, you don't really need to know the previous states, right? That doesn't mean that the previous states are independent of the next state. Given that you know the current state, you don't need them, right? All the information are carried inside state ST, right? So you start from one state S1, you just change to S2, S3, and so on. Then you get to a state ST, right? When you are here, you don't really need to care about before. You just look at the current state, and you would say, OK, this is the chance of going to the next state, every possible case, right? So, and if you consider this fact, then you can simply write down the rewarding and transition function in the form of a probability, conditional probability distribution. So what was the reward, transition function? It was a random function, which starts from the state that you are in, the state ST, and the action AT, the action that you are in right now. So you have a pair of state in action, and it's going to tell you what is the next state, right? You're going to give you a random transition to the next state. Same thing is for the rewarding function. So it's going to look at your current state and current action and going to explain you what is the reward, right? What is the chance of every single reward that you could get. And you can just use these, represent these two random mappings using a conditional distribution, right? So how you can do it, you could say that, well, say that I am in a particular state S0 at the beginning, and I do action A0, right? Then upon doing action A0, I'm going to jump stage, right? It's going to be S1 and R1, right? And then again, I do one, for example, I do A1, and then I go to the next state and reward, right? And I keep on going like this. Now, if I want to describe the reward and state at particular time t, what do I need to write down? How does it look like? It's going to be the probability of this pair given the last state that I was in and the last action that I have done, right? So in particular, if I am in particular state t, I do action AT, and then I'm going to jump into the next reward and the next state, right? And then I can simply define this starting from here towards. I can just define it with this probability distribution, conditional probability distribution, right? Everybody agrees? Questions? So what is this transition? It's going to tell me that, say I am at one particular state S, right? Right now. And I do a particular action A, small a here, now, right? Then what is the chance that I get into a new state, S bar, right? So from one state, I'm jumping to a new state. Now, one question. This yellow S bar, can this be same as this small green S? Can it be the same thing? Yes, it can be. OK, great. So you're seeing it. And it also gives me a probability distribution on the. I do know that the notation might get a bit confusing, but from now on, whenever I feel that it's OK, I'm going to just compactly write it down in this form. But no worries, since I'm a super obsessed person, I am usually explaining things in detail. So it's not going to be that confusing, but whenever you feel confused, just ask me. But I mean, if I want to use this notation for the rest of this chapter, you're gonna just be super unhappy, right? So now, now I am at this particular time t. Now, if I go one time back, right? I want to know, for instance, what is the probability of previous time, in the previous time step, what is the probability of getting particular reward R and transiting to particular state S bar, given that 2 times ago I was at S and I did action A? How does it look like? It's going to be exactly like as what we had on the first line, right? So say I start in the terminal state, right? And I do one particular action, right? I'm going to get back to this terminal state, right? If I again do the same action, I'm going to get back to this state, right? And I'm going to keep there, right? Now, if I am in another state and I do one action, and then I get into, and I keep on going till I get to the same state that I started with, right? So I just loop all the way to get back there, right? If I do the same action as I did at the beginning, the next state in action distribution is going to be the same again, right? So the thing that I want to indicate here is that this time index is no more that important. I mean, the order is important, of course. The next state is described by the previous state. But if the next state is st, then you just need as the previous state st minus 1, right? As long as you put the same small letters here, R, S bar, S, and A, nothing is going to change, right? So if I keep on going down, it's going to be always the same expression because this is a Markov process, right? So it doesn't matter if this is the time index 1 or time index 100 that I am in this state. As long as I am in this state S and I do action A, the probability of the next state and the reward that I'm going to get is going to be unchanged. It's going to be the same thing, right? Everybody's cool? Questions? Yes? Yeah, the fact that I'm, like, here is P of R, S bar given S and A, right? And I don't care that this S, the green S, was happening at time A and action was at time A, right? If I am at time 0. If I'm at time 0, then this R and S bar is going to be the pair at time 1, right? If I am at time t minus 1, this is the pair at time t, right? And so on. So it doesn't matter which time you are in. Does that make sense? Okay. Yes? R and S bar are not independent of each other necessarily. It could be, yes. Typically is the case that the reward only depends, I mean, in many environments, reward only depends on actually ST plus 1. Like RT plus 1 only depends on RT, ST plus 1. But in this formulation, no, they are not independent actually. No. But I mean, typically it's the case that they are like, when you know this green guy, you can just, yellow guy, you can just throw away everybody else. Typically, not all the time. Yeah. Questions? No question? Okay. This guy that you see here is what we call it a Markov decision process. Yeah? Why it is Markov? Because every single time it only depends on the previous one, right? Not everybody else. Like, it's important to pay attention to this. Like ST plus 1, of course it depends on S0 as well, but as long as you have ST, you don't care about S0 anymore, right? So the information is just carried out. It's a state-dependent system, right? Okay. Now, what we consider here in this chapter is that we work with a finite MDP. Now, can we work with infinite MDP? We can do it, but eventually this chapter is only to give you the background. So I don't want to just dig too much deep into this one, because at the end of the day, like model-based approaches are not that much sophisticated. Like you hardly get any model-based environment with the model now. So we're going to stick to the finite MDP. And why the finite MDP? I simply mean the assumption that we started with. So the rewards are coming from a set of few options, right? So now, if you have a continuous state, one way to do it, you can approximate it by just quantizing it, right? This is one way if you want to stick to this one. But those guys have their own framework as well, which we're not going to really waste time on that. Okay? Now, the key factor about the MDP is that your MDP is going to be described by this pair of by this conditional distribution. This means that the only thing that the environment, so you throw away the environment, and the only thing that is remain from the environment is this probability distribution. Now, one thing that you might ask me is that when you define the the RL framework, you said that we have a rewarding system and we have a transition system, right? But now you're representing things with one joint conditional distribution, right? So you're talking about R and S bar, the next reward and the next state given the current state in A, but we expected to have one separate transition for state, one separate transition for reward. I guess this is quite obvious for you what you need to do in order to get there, right? What you need to do if you want to just know the transition, you don't care about the reward. What should we do? Say I only want to know the distribution of the reward. I want to describe the rewarding system. I don't care about the next state. What should I do to this guy? Not average, but sum over all the next states, right? So what you're going to do, you're going to marginalize the state, right? You see it. Yes? Does that make sense to you? Everybody's clear? So this guy is, the point that I want to tell you here is that this guy is giving you much more sophisticated description as what we had in the original formulation. So in the original formulation, I told you there is one rewarding system, right? And this is going to tell you what is the reward given every state and action pair that you have, right? Now, if you want to get there, you can simply just marginalize this one over all this state. Like you would say, okay, the reward when I am at this state and do this action is going to be, the distribution of the reward is going to be this if I consider the next state to be state 1, is going to be that if I consider the next state to be as state 2, and so on. So you just add them up. It's going to marginalize everything. This is going to be your rewarding system, right? So the rewarding system is immediately coming out of the distribution. Everybody's seeing it? Because I don't know, maybe I am too tired and I started to be a bit paranoid. The feeling that you are not asking any question, and this is a bit weird. Everybody's cool? Yeah, just go ahead. We're going to see it. We're going to see it. Sometimes you want to, for example, take expectation of your reward. Like, what is the expectation of the immediate reward? You don't need to know the next state, right? But you can always explain the transition model, right? You can always say that, okay, if I sum it up over all possible rewards, then I'm going to get rid of the reward, and then you're going to be only the next state, right? So you're going to have the probability of the next state given the current state in action. Yes? Sorry? Questions? Yes? This one? This? What is the, sorry? Yeah, it's going to tell you what is the chance of every single next state, right? So I am in state 1, right? The first cell. Then I decide to do action right? Then I'm going to change this state, right? It's going to tell me, okay, the chance of any of the possible state is like this when you do action 1 at state 1, right? I'm going to give you an example, then you're going to get it clear, right? But this is actually the only thing that I need in order to describe my environment. If I know this, then that's it, right? This is the whole thing about the environment. No. Questions? No question? Yes? Okay. The reward is here random in general, right? Because like in the frozen lake, right? In general, it's a random. What we are doing here, this guy, where is the distribution? The distribution that you have here is going to tell you, like, this R that you see is the reward that you are getting in the next time step, right? And it could be from possible cases, right? It's going to tell you what is the chance of every single case and what is the chance of your next state being any possible state, given that you are in the particular state S and you do the action, right? So here this rt plus 1, the one which I showed with capital letter, that one is a random variable, right? Because like in the frozen game, frozen lake, sorry, when you want to just move right, you might sleep, right? And then you might get another reward. So you can think of the reward to be something random. So it happens with some probability to be 0, with some probability to be -1, right?
Are we saying that random variable, that sum we have, that's rt plus 1 as well?
Sorry?
Are we saying that sum we have, the sum we just showed?
Here, yes, that's going to be. Now, here what I'm doing here is like you would say, okay, I'm in this state, in this cell, and I do this action. I don't care about the next stage, right? I just want to know what is the distribution of the reward that I'm going to get after doing that action, right? So if you just compute this marginalization, it's going to give you a distribution, right? And this is only distribution on R, right? So it, like in the example of frozen lake, it's going to be the possible cases for R is going to be -1, 0, 1, right? And then this distribution is a categorical distribution with 3 entries, right? No. Question? No question? Yes, go ahead. Okay. Yeah. So yeah, let's just do this example. I'm going to keep this example for the rest of this chapter because this is the dummiest example we can solve. So if I want to do more than that, then I'm going to get into trouble. But here, this is like a super dummy one. And the game, I just called it Dummy Grid World. So what is the story? The story is that you want to just start, you're at any cell. You want to get into this top left cell with the shortest path possible, right? And you might think of it super stupid, but there are still very stupid policies, right? Say I am here. I can go down, then left, then up, right? Then this is not a good thing, right? So you want to just go left directly to get to the destination, right? So anywhere on this grid world that you are, you just look for the shortest path towards the corner. Okay. Now here, this if you want to just write down this RL setting in the form of a formulated in the RL framework, you need this state. This state is simply like the frozen lake, right? It's going to be the cell index. So, for example, this guy is 0, so it's going to be 0, 1, 2, 3. It's one of the possible states, right? And what are the actions? The action are the direction that you are going to move. I'm going to keep the same notation, so you can just move left, down, right, up, and then I just index them from 0 to 3, right? So these are any action that I do. And then what is the rewarding system here? So if I move to another cell, so if I am at this cell and I do any action, that it just moves me to another cell, the thing that is going to happen is that I'm going to collect reward -1, right? And then it makes sense because I'm looking for the shortest path, right? So if I am here, top right, and then I want to find the shortest path, then I just move 1 step, right? And it's going to be -1. Reward -1 is definitely larger than going down, left, up, right? Because it's going to be -1, -2, -3, right? Everybody's clear? Now, this is one thing, but if you are here and then you hit the wall, okay? Then you're going to collect -1/2. Whenever you are in any cell and you move to the direction which you cannot go to another cell, you're going to get -1/2. And you might tell me why you don't put it 0. If I put it 0, it's going to remain there forever. I don't want that, right? Because if the agent is here and each time it hits the wall, it's going to get 0, then it's going to keep hitting the wall forever, right? Because hitting the wall forever is more worthy of just moving 1 step, right? So that environment makes sense to you, right? So now, looking at this one, now I want to just explain or describe this rewarding transition model that we have. So the thing that I want to do, I want to know, what, for example, what is the probability of the reward and the next state, given that 3. So look at going to be the next state? 1, right? What's going to be reward? -1. Is there any randomness here happening? No. So I can describe the distribution like this, right? So R and S bar, the reward that I get, it's -1. Next state is going to be 1. This happens with probability you think of is going to happen with probability 0, right? Everybody? Yes? Does that make sense? Okay. Now, what if I'm at particular state 0, so here, and then I do any sort of action? What's going to happen? This guy is terminal state, right? So this guy is the one where the game is over. So when the game is over, when I get into that state, I'm going to remain in that state, right? And the reward that I'm going to collect is always going to be 0, right? So now, when I am at the terminal state, no matter what the action is, the next state is going to remain the terminal state. That I'm collecting is going to be 0. This happens with probability 1. Anyone else happens with probability 0. Everybody's cool? Good. So now, yeah, S equal by 0 is the terminal state here. Now, one cool thing about this way of thinking is that we can actually show everything in the form of a transition diagram, because when we have a finite number of sets, we can think of different sets, and then depending on the action that we're going to do, we might stay in one cell, or we might jump to another cell, right, to another state. Now, is it okay that I keep on with this one, just extra 5 minutes, and then give the break? Yeah? I just rushed up to just get here. This is what we call the transition diagram. This is sometimes much easier for you to just represent everything in this form. Say, for instance, I have 3 different possible states. So a state 1, a state 2, a state 3. 4 different states. These 3 states and the state S. And when I am in this particular state, depending on the kind of action that I'm doing, say I do action 1, then I'm going to change this state from this one to another, right? I'm not showing the complete diagram because this guy has also its own directions, right? Maybe from this one, you get into this state, and so on, right? But every direction that you show is going to essentially present the kind of transition you can have from one state to another. Now, let me do this for this particular example in a grid world, and then it's going to get much easier for you to understand it. So we had 4 different cells, right? 0, 1, 2, 3, correct? And now, if you think you are in any particular state, any of the cells, depending on the action that you do, you can change your state, right? Clear? You can change your cell. And then you can describe it by using only these 4 different states. For example, if I am at state 0, it doesn't matter what I'm going to do, I'm going to always return to state 0, right? It's the terminal state. So it's going to be a loop here, and then I get the reward 0, right? What if I am at state 1? What's going to happen? When I'm in state 1, I can jump from 1 to 0 if I just do action 0, and I collect reward -1 step. I -1, right? And then one thing else, I haven't shown it, but we should also have a kind of inner loop as well. Because when I am in 1, if I do any other action, I hit the wall, and then I get -1/2, and I get back to my own cell, right? So I can just show it with an inner loop. I have missed it. So maybe I put it here, but I don't know why I haven't shown it here. Now, another thing that for example, cell 2, state 2, when I'm here, when I do action 3, I go up. I get reward -1. When I do action 2, I go to right, and then I collect reward -1, and again an inner loop, right? And you can do the same thing for state 3, right? So now, what you all have as the Markov decision process is the probabilities of all of these arrows that you see, right? So you have different states, and then it's going to tell you what is the chance of you moving on this arrow, what is the chance of you moving on another arrow, and so on, right? Everybody's clear? Questions?